Welcome to Data and Biotech, a podcast from Cordi where we explore how companies leverage data to drive innovation in life sciences. Every 2 weeks, we sit down with an expert from the world of biotechnology to understand how they're using data science to solve technical challenges, streamline operations, and further innovation in their business. Here we go.
Welcome to Data and Biotech. I'm Ross Katz, data science lead at Corden. There's a growing assumption in biotech that if you throw enough omics layers into a model, clinical breakthroughs will follow. But the reality is that integrating multimodal biological data is full of pitfalls that can quietly compromise the quality of your predictions and your science. Arvind Rao is a professor of computational medicine and bioinformatics at the University of Michigan, where he leads work on merging multi-omic data sets for cancer research and has built AI literacy programs designed to help healthcare and pharma teams to better evaluate AI tools on the market. Arvind, welcome to the show.
Hi, Ross. Thanks for having me.
Awesome. Well, just to get us started, you sit at the intersection of computational biology, clinical oncology, and AI education. Can you give us a sense of the landscape you operate in and what your day-to-day research looks like right now?
Sure. So, what me and my group tend to be doing most of the time is trying to answer a really fundamental question, which is how can we set trust guidelines in the context of biomedical AI? And this becomes a very multidimensional question because it's not just about building the right models with the right kind of data, but it's also about taking the outputs of those models to then biologically credible or clinically credible inference. And so that's really the question where we start is how can we actually trust biomedical AI algorithms? And that leads us to working across pathology images, spatial transcriptomics, bulk RNA-seq, single cell data, not just to build models, but to understand what information is real, what's recoverable fundamentally, and what's just noise dressed up as signal. So we also look a lot at reliability, credentialing, and model veracity. And as I'll say a little bit more as we go on, is trying to understand the complete life cycle that goes from data to model to inference and probably even feedback from each of those three different spouts back to how we do things better. So that's one part of what we do. In parallel, I also work with the pharma and healthcare teams to help them evaluate these systems critically because the bottleneck right now is not the models, it's in the decision making under uncertainty. And so, because not all modalities are available simultaneously all the time for every single patient, a lot of these decisions have to be made when full information is not available. And because the calibration of those sources feeds into how one would meaningfully make decisions, that's another thing that we work on quite a bit.
Awesome. So, touching on the kinds of data that you work with and how you combine them together, we're talking about multimodal and multi-omic data integration for cancer, and we've seen that your recent work spans H&E histopathology, multiplex immunofluorescence, spatial transcriptomics, single cell RNA sequencing, as you were just talking about. So, for listeners who may know some of these but not all, can you just briefly touch on what each of these data types show and what the integration problems are when you try to combine them?
Sure, that's a great question. So I think I'll step back for just a little bit to communicate to the audience who may not be from biology or clinical sciences to tell them how unprecedented a time we are living in at that's current, which is that biology has become extremely quantitative. We have almost paralleling, perhaps astronomy at a scale that's blowing up as we speak, which means you have access to a lot of modalities, a lot of technologies that let us go all the way from, tissue organization to cells to subcellular and information about proteins and genes and all these different constituents. So it's really a multi-scale, multi-phenotype, multi-omic problem that has really become the lingua franca for biology, which means that the ability to understand these disparate yet correlated views, making sense of this data, trying to understand the biological or clinical picture, the pathology, if you will, is all becoming extremely quantitatively grounded. So it's a great time to be a data scientist in biology and clinical sciences. With that said, I'll then get into these modalities you asked me about, which is that each modality, like we just said, gives you a somewhat different view of the phenomenon, which could, in our case, we work in oncology. So I'm talking about things in the context of cancer. So every modality gives you a different view of the tumor. H&E images, which have been around for more than 100 years, show structural and morphological aspects of disease. How are the cells? Are they atypic? Are they weirdly shaped, etc.? We can get that good sense from the H&E images. And we can now take pictures of those images as well, digitized, and you can do lots of interesting image processing with them. Single cell RNA-seq is a more recent development. Not too recent, but again, definitely in quite recent, which gives you a look into these different cells and their states at very high resolution. You can get close to, anywhere from 5,000 to 10,000 genes and their expression recovered from every single cell in your tissue. Spatial transcriptomics takes that one step further and says not only will it tell you what's in the cell, it will also be able to orient you in terms of where's that cell located related to the pathology of the disease. So you can actually get a sense for which cells come together, which cells tend to be separated, are there histological manifestations within which these cells tend to express themselves or be prevalent. And a somewhat lower cost variation of that is multiplex imaging, where you may not want to get information about all the genes or all the proteins, but some selected few. And so, if you know what you're looking for, multiplex imaging becomes a very good way to understand which cell types are present, how are they oriented in the microenvironment, etc. So, talking about challenges, because these are overlapping yet disparate views of the tumor, I almost liken it to remote sensing or satellite imaging, right? You can get hyperspectral images of some very, very few areas in deep resolution, excellent spatial resolution, excellent wavelength fidelity. But that's very expensive. You can't do that all the time. If you do the traditional multispectral or the low res kind of satellite imaging, then you can get a lot of data, but not at that resolution. And so the ability to be able to meld these two different scales of data to be able to reconstruct the biology becomes really critical. So one challenge is these images don't align naturally. One has to look for coordinate free approaches to be able to put these together. Second is despite these images being fantastic and in a lot of ways unprecedented in terms of insight, they can differ quite a bit in resolution, noise characteristics, sampling biases, batch effects, and even the context of what does signal mean relative to noise. So it's not just a simple matter of integration when we use that word. It's not just simply stacking data. It's reconciling these fundamentally different representations of biology. And that's kind of where the effort is currently oriented. I hope that helps.
No, I think it definitely helps, and I'd love to dive into some examples of your work to sort of illustrate how you're using these different modalities in your work. So, that there's two recent papers that you shared with us, both of them published this year in NPJ Artificial Intelligence. I think they tell a really compelling story about sort of how you do this these coordinate free approaches to data integration that also surfaces the biological context and allows you to draw like really verifiable conclusions about what's going on. So if it's okay with you, I'd like to start with SPIFEE. So my understanding is that you've got most graph-based approaches to looking at the tumor microenvironment represent the relationship between two cell types as sort of a single number, as a distance or an interaction score, and SPIFEE replaces that with an entire function. So can you explain what information you integrated into that and what we were losing before, and then what SPIFFE allows you to capture and utilize that you couldn't previously?
Sure. And that was a very good articulation of paper. Thank you for bringing that up. Before I get into SPIFFE, I had to, a shout out to the student Ashley Sang, who did the work in leading us on this paper. So it was really her hard work that brought it all together. And the question that we sought out to ask was that, like exactly like you said, given the exquisite spatial resolution of these platforms at revealing not just what cell types are there in the environment, but how they are oriented relative to each other, the prior technologies that we were seeing were mostly looking at summarizing all of that complexity with a single number, which meant that if things are heavily infiltrated, heavily mixed, you are kind of summarizing it to a single number because it made the downstream analysis and statistics easier. But we felt it was a little bit too reductive in the sense that there are patterns to these spatial infiltration. So maybe two cell patterns are mixing with each other, but the extent to which they mix might have some a spatial component to it, which means it might not be uniformly mixing, it might be mixing in certain pockets, but not everywhere. So that's a very different visualization than uniform mixing. And unless you can go beyond looking at a single number that summarizes all of this complexity, you're going to be losing out on the insights that you could get. So with that in mind, Ashley and I set out to sort of ask the question: what if we used a measurement that looks at not just the amount of mixing, but where that amount of mixing happens, and can we express that as a function in space? And so what we came up with was an abstraction where we had a graph. So we could leverage the graph neural network paradigm. But the graph was now not just simply nodes and edges, both of which were scalar, but the nodes could be vectors, which gets at the complexity of the cell identity, and the edges could be functions, which gave us this notion of what is the spatial pattern of intermixing between any two of these cell types. And so you could express that very compactly with a graph, but now adding this functional valued edge on top. And it did take us a little bit of work to get to repurpose graph neural networks from scalars or even vectors to functions, because it's not a trivial jump to do that. But I think thanks to Ashley's persistence and hard work, we were able to get to a point where these objects can now be analyzed en masse, and we can get a much better sense of spatial infiltration between tumor cells and different kind of immune cells, both statically and dynamically over space, and use that as a way to get signatures of how these relationships change, and if those changes in relationships can be potentially prognostic or predicted. So that was the goal that we sought with the SPIFEE paper.
Yeah, can you give an example of of where that kind of intermixing logic exists and sort of like the types of conclusions it allows you to draw?
So practically anything about cancer is about the microenvironment, which means we talk about, everybody in the field agrees the one of the fundamental hallmarks of cancer is immune modulation, which means you've got this plethora of immune cell types in the microenvironment which get recruited in very interesting ways when there is this fight between the invading tumor and the resisting host. So each one's trying to do their thing. And this push and pull mechanism now creates this sort of very dynamic picture of how these immune cells are oriented relative to not just each other, but also to the tumor. And so pancreatic cancer is one example that we use in the paper. But anything to do with microenvironment automatically falls into this scope. One can then talk about figuring out how do these spatial differences, when we use this kind of SPIFEE approach, how does that reveal insights into the biology of the disease that we couldn't have gotten otherwise? So it's not just the interaction, it's the structure of the interaction in the microenvironment which can distinguish different states. So in the case of pancreatic cancer, one can, for example, distinguish chronic inflammation from cancer, or a intrapapular mucinous neoplasm from a more aggressive cancer. So this has implications to understand the stage of disease in ways that we at least were unable to find elsewhere.
I found the paper really interesting, and sort of like the way that you're constructing the models allows you to identify not just what is happening or what the predictive outcome is, but where it's happening, and then dig into the how, which then allows you to ask, how is it happening? And so this is sort of like the beautiful marriage of sort of deep biological understanding and algorithmic approaches that allow you to get to where to focus your attention much faster. And so from sort of a high level, healthcare lens, it's, using computationally efficient approaches that allow you to focus the most limited resource of all, which is, like expert attention on the problem that might be going on with a given patient. Am I thinking about that right?
Absolutely. And in fact, it speaks to the notion of, I think you already brought it up, but interpretability becomes then a part of the conversation. And then you then have the ability now, because you can also get images that are sort of stacked in space and say, this part goes for immunoprofiling, this part goes for spatial transcriptomics. Now you can start interpolating between the two to ask the question, what are the molecular drivers for these distinct patterns of spatial infiltration? So now you get a chance to go from observation to mechanism, and hopefully that reveals something about disease biology that we wouldn't have otherwise been able to appreciate.
Yeah, so with that in mind, I want to jump to your second paper, which takes sort of a different but complementary approach. This paper starts with pathology images like H&E slides labeled with the clinical outcome, and then you're using those to discover the morphological patterns associated with drug resistance, and then mapping those patterns onto spatial transcriptomics, and then you're ending up with drug targets. So can you sort of walk through that entire logical progression from how you get from, a stained tissue slide to recommending a CDK inhibitor?
Sure. So, just before getting into it, I want to, call out, our brilliant graduate student, Reva Kulkarni, who sort of led the work. And what she wanted to ask was the following question. If you have HAD images from patients and their corresponding outcomes, either as a consequence of treatment or what happened to them eventually, that's a very robust set of data for which you have both the imaging and the outcomes available simultaneously. And HND images are the lingua franca of pathology. Getting them has been fairly standard, and the price point for HND images is a very, very affordable price point. So doing it at scale is not hard. For some subset of those HND images, one can then go and try to do spatial transcriptomics. And because the price point for spatial transcriptomics is, at least 2 to 3 orders of magnitude more, right? It's impossible to get the same volume of data having both the HND and the spatial transcriptomics. I will use the abbreviation ST for spatial transcriptomics. And so, because you don't have this tripartite combination of high ST data, high HND data, and high outcome data, we need to do something smart about borrowing intelligently. And what do? We say, well, as a first pass, let's use this combination of HND data and outcome data to find those morphological patterns that are most associated with outcomes, whatever you're interested in our case, treatment resistance. Then we can say, looking at the patterns identified in those HND images and the companion ST data, what is the interplay between the ST derived molecular mechanisms and the patterns that were found to be associated with those disease level outcomes? So this lets us go between these three vertices of the triangle, so to speak, but leveraging what's available. If you did it any other way, you would have just a huge sample imbalance between the ST data and the outcome data, right? You in the order of the order of magnitude would be like almost 2 to 3 orders of magnitude because the price point comes into play. So when you do it like this, we can then nominate molecular mechanisms and hopefully actionable targets that can then connect us to why does treatment fail, what's unique about this patient, what's the molecular mechanism responsible for it, and what drugs might be best capable of modulating things to become more favorable. So this is the approach that we took in linking up these different modalities, but which had also vastly variable numbers of samples to go with it. So that was our engineering sort of trick to go between these three and still get something useful.
Yeah, so if I'm recalling correctly this paper, correct me on anything that I'm missing, but there is sort of a portion of the modeling exercise where you're using a generative adversarial network to like use the H&E slides to reconstruct what we believe the spatial transcriptomic profile would look like in that case. So I'll stop there, and then is that right? Am I remembering that correctly?
Yeah, so I think the way we thought about it was, GANs, generative adversarial networks, can be used in a variety of different ways. One is of course, for augmentation of the data, for synthesizing, examples that look like it without necessarily being new ones. So we used it more in the processing chain, not for any specific mechanistic intent, but more as a way to be able to build this tripartite workflow in a more harmonious manner.
Yeah, and then another aspect of this paper that I found really interesting was sort of the multiple instance learning approach, where you were segmenting the slide images and then utilizing the attention weights from the model that you're training to identify the patterns in the different instances that are associated with a clinical outcome of record. And then what that allows you to do is sort of to interrogate those portions of the slide instance, or in the case of validating your work, go to a domain expert in oncology and have them sort of like ask the question, what's going on in this portion of the slide, so that you can then verify that actually the model is in fact picking up on real biological mechanisms that influence what's happening there. Am I remembering that correctly, or how would you fill in the gaps of that?
Absolutely right. And but I also want to point out that we sort of as engineers, we built on top of things that have become a lot more available. And some of the some labs have been very nice about being responsible citizens for science, and that they put out very good software that we can then build on top of. So the idea of the attention based identification of interesting regions and the MIL actually was built on top of this tool called CLAM from the Mahmood lab at Harvard. And so they've been fantastic at putting out solid reproducible code. So we built on top of that. So I can't take credit for the part of the MIL genius and putting that into this framework
Of course.
and finding useful patterns, but we built on top of that to then go to regions that were implicated in treatment resistance, and then mapping that back to ST data to be able to understand why do we see what we see.
Right. So then after you answer the question of like, why do you see what you see? My understanding of being able to map it to the spatial transcriptomics is then you're able to nominate, because you have sort of the what's happening genetically, you're able to map it to specific potential targets that might be implicated in the biological mechanism, and then you're able to interrogate sort of like what are the drugs that are in existence today that might be able to be utilized to inhibit those targets. Am I thinking about that right?
Absolutely. So the good again, the part is again, I keep coming back to this. Perhaps that as engineers, we build a lot of things on top of what's already available. So again, the idea of trying to go from the molecular mechanisms prioritized to networks was again done thanks to a variety of different tools, both open and commercial, that we were able to leverage to say, well, people have already taken the trouble and done the hard work in trying to organize things into pathways, organize things into terms of which drugs affect what pathways. So we can look at these databases and begin to put it all together to say, what's the connection between this nominated pathway and the target and the drug that we want to go after. So definitely a lot of, community help has been there. And so we want to be clear that, just hope that this excellent spirit of collaboration continues in the community, because then we can build off and riff off of each other to be able to build tools that we can then eventually use to help patients. So I think it's a great example of good quality tools being made available publicly, and then others building on top of them to be able to answer questions. So I think, yeah, that's where we are.
Yeah, and but also understanding sort of what are the data sets that are available, what are the tools that are available, and how do you stitch the tools together in a way that is sort of methodologically rigorous in order to allow you to do something that is computationally efficient but can also be validated from a biological perspective. And so your work feels like that is generally there.
Yeah, and I think you mentioned right now in passing something extremely relevant to even what we are seeing in biology right now. You're seeing a lot of solid work tending to go towards multi-agentic workflows, those kind of things. You can basically spin up a whole end-to-end pipeline that threads together, in using your words, multiple agents that do different things. But because if the discipline around ensuring that these things are not cross-calibrated, they don't talk about the same mechanisms, they don't do things the way they ought to be done, then it's very easy to, you know, amplify the noise and not the signal. So I think in just what you just said, there is a very deep insight and a lesson that when you start building these multi-agentic workflows in the context of all the amazing AI models today, it's probably even more important to understand where these models were manufactured, where they went to school, what kind of architecture was used to train them, and to ensure that there's an impedance match between these different workflows. Otherwise, garbage in, garbage out.
Yeah, for sure. And that, I mean, that brings me to another question, which is sort of, when you see either your students or other people in the community, trying to merge these different data types together and bring them under like a single predictive framework, maybe with, agentic AI in the middle. What are the common mistakes that you see? Where do things tend to go wrong?
That's a great question. So I think the key part is that it's like it said, when you start putting these things together, I think the what we've learned is that the power of collaboration, and that we are very cognizant of the fact that we don't have some of these very deep knowledge pools to be able to understand where the noise might be springing up from. So understanding, talking to the data acquirers to ask where's the noise, what could be the different batch effect parameters, etc. That becomes really important. And then you have to pre-process them in ways that again match to the structure that these models then ingest. So that engineering is non-trivial. Then once you use the models and you come up with a prediction, I think thinking about calibrating that prediction with some concept of uncertainty that could be either data based or could be model based or even plausibility based, right? You need to have the sniff test, which is to ensure that what you're getting is plausible. And that's where again collaboration with a domain expert becomes really, really important. And then once you made the inference and you've got hopefully some measure of uncertainty, that uncertainty measure can then be used to inform how best to do the next experiment, how best to design the next model, how best to acquire data that is most amenable to improving the model. All those questions come up. So I think from the perspective of building gradually better models, I think the scientific method and its relevance becomes even more pertinent than what we've seen in the past with the use of AI.
For sure, and thank you for that. I think that people, we're in an environment where the AI tools that are available make it easier than ever to sort of boot up whatever sort of modeling software is out there, and believe that you can prompt Claude into or ChatGPT into curing cancer, and sort of the nuance of how that gets approached is really important. But returning to your research, the two papers that we just talked about sort of feel like complementary pieces of a larger vision. There's SPIFEE building richer representations of how cells and pathways interact spatially. And then you've got this multimodal framework that connects the spatial patterns to molecular mechanisms and drug targets. Am I reading that correctly? Is that sort of the vision of where this is going, or where does the overall pipeline of your research and your students' research go from here?
So now that we have so many more, in general, just the, what we used to call average ability has now gotten amplified beyond our wildest expectations. And so what used to take months to code up a workflow now has, become a lot more accessible. You can build on the power of compute. You can essentially stand on the shoulders of giants and you can look at all these GitHub repos and build up a new framework pretty quickly. So we said, well, with all that's happening, what's the place that we can perhaps have the best impact? And that would be, well, let's now start building different pieces of this overall pipeline and see where it needs to go from biological understanding to biological insight to interpretation to then the clinical and translational component. So all these two papers that we discussed today are essentially, getting at this part in two pieces, which is one part builds better representations of the spatial biology. The other one connects those representations to mechanisms and interventions. And so the long-term goal is a pipeline where you can go from tissue to mechanism to decision in a way that's traceable and defensible. So that's kind of where we are trying to put all these pieces together.
Yeah, that makes a lot of sense. And just to tease that out, my understanding is that because you're reconstructing this much slower and also much more expensive data in spatial transcriptomics from, sort of the H&E slides that are widely available and very inexpensive, you're sort of building and you're paying very close attention to sort of the traceability and like the inferential rigor of how the decisions are being made. You're setting up a stage where, computational tools using existing data can enter the clinic and can, enable practitioners to be that much more efficient and effective at understanding what's going on with a given patient and understanding sort of the likely impacts or sort of assumptions and caveats that need to be kept in mind when potentially prescribing an existing drug or a new drug to a particular patient. Am I reading between the lines too much here, or am I understanding where things are going?
You're doing great. You
Okay,
beautifully put. Everything that you've said is completely in line with exactly what we're talking about here. Yes.
awesome. Well, to switch gears a little bit, since you're advising clinicians and hospital administrators on AI, you've described yourself as a cautious optimist about AI in this space. So can you describe what specifically makes you cautious, and where do you see sort of the most excessive exuberance relative to what the evidence supports in terms of how AI is applied in the computational biology space?
That's a great question. So thinking a little bit about that, I think just personally, my biggest concern is that perhaps we are very good at demonstrating capability, but not reliability. So we are very good at saying, okay, this can be done. And then we show it, it can be done. That's the paper and that's great. But the translational gap between what that paper shows to a reliable product that can be used every day in the lab or in the clinic, I don't see that happening as much. And I don't know where that's coming from. So what I'm seeing is we are building impressive models. Each one's got a billion more parameters in their models. Each one's got a more bright and bushy data set. But the concept of trying to go from those predictions to being able to consistently trust them in some very high stakes settings like healthcare presents, I think that part, I think we could do a little bit more work on. So what I mean is the metrology of AI, right? You take a simple ruler, you take a slide rule, you take a calipers, whatever it is, right? You make a measurement, and we are very good at being able to say, well, your height is, I don't know, 5 feet 7 plus or minus so many inches, right? You're very good at because those things matter, right? And when I make predictions and I don't have a error bar to go with it, there's no metrology to go with it. What do I do with that prediction? If your prediction is this person is COVID positive with a 3% error rate, that's a very different thing than saying this person's COVID positive with a 50% error rate, right? What do you do with that? So I think COVID positive status is helpful, but accompanying that with some calibration of what that prediction is associated with, that becomes really important. It also feeds into reliability, right? It's not very helpful when you say that the stochasticity that we normally associate with AI can give us results that are all over the place. Run your favorite generative AI engine twice, right? And unless you are very deliberate about the prompts that you use to ensure that there is consistency, you can get vastly differing results. Not because that's magic, because that's math. Generative AI, by its definition, is generative. It samples from a distribution. So the variability that you're seeing as a result of using it is very natural. But you can't have that kind of variability when it comes to treating patients, right? So when you start building these workflows that have multiple generative AI agents all threaded to each other, it becomes really difficult to talk about credentialing and robustness and uncertainty propagation and error propagation. So I think that's where the real work is. Like, I think capability demonstration is very nice, but I think we need to be more deliberate about how we test these things in real world settings responsibly to ensure that they then get to a level of quality that you can deploy them.
Yeah. So getting to the idea of sort of evaluating, there's a lot of foundation models for biology that are coming out, which they're getting a lot of attention and investment. How do you think about evaluating whether they're advancing clinical utility or just, sort of gaming the benchmarks?
Yeah, so I think this kind of almost reminds me of a interesting law. I think it's called the Goodhart's law. It says that when a metric of performance becomes your cost function, it ceases to be a metric, right? A metric evaluates performance after the fact. If you use the mean square error or some version of that in your training process itself, then it's not even the right metric to evaluate your algorithm by. So I think we fall into that trap a long time ago. And so I'm really curious to see what we can do to get out of that trap, because then you have to ask the question is, well, you're chasing the accuracy metric because that's what everybody likes to see. But what information are you actually extracting? Are you extracting signal, or are you extracting artifact? How does performance degrade under real world shifts? I just said that, simple things, right? A different scanner, a different protocol for building an H&E slide, or some stray marks, pen marks, or tears, or glass breaks. All these really quote unquote trivial things can really massively impact the quality of your prediction if you didn't are just for those confounders going in. So when you build an algorithm, is it built on some nice pristine data set, or are you actually using the real world confounding information to build a more robust model? That's the second thing I like to ask. And the third thing is, does it actually change a clinical decision in some tangible way versus just being a benchmarking exercise? Like, I scored 5 points more than you on AUC, which I'm sure is super interesting and useful to have. But did it tangibly change something for the patient or how you would deliver care? Right. And that then brings you to other points that become real world questions during deployment. I mean, people have already shown this, right? Like you had this sepsis algorithm, that could detect the onset of sepsis quite early, but it began giving so many alerts so often, it led to alert fatigue, and basically the people in charge just shut it down, right? So that's the real world problem, right? And so going from building an algorithm that meets some benchmark to actual deployment for value, they're different asks. And so if you can't answer these questions, you are likely falling into a type of potential hype and not real utility, right? So when you have all these great foundation models, I have to ask the question, what is the difference in the information that you're recovering that truly justifies this additional billion parameters, right? And if the change in the vector is not that much, you have to ask the question, well, then what purpose is it truly serving? So that's kind of where I'm coming from.
Yeah, that makes a lot of sense, and that maps to a lot of my experience with machine learning and AI projects. It's fundamentally, if you're not, if you don't know what decision this is going to change and how it changes the quality of that decision, then the quality of the model is fundamentally impossible to measure. Like it's great that I seemingly know a lot more information about what's going on in my environment, but fundamentally, if that doesn't change any of the outcomes, then even if the information you've given me is factually accurate, it is, irrelevant. It's noise from the perspective of the goal that I'm trying to accomplish. So yeah, that makes a lot of sense. So you've been building AI literacy programs for healthcare professionals and pharma teams. Is there a core gap there that you're trying to close? And what does that gap cost when it goes unaddressed?
Yeah. So I think what I noticed is that, I've been on both sides of the table in some sense, both in terms of model articulation, but also procurement. So the thing that I was observing was that there's basically a gap in the articulation of what it takes to go from a model that meets all the benchmarks and the metrics to deploying them. So what I was seeing was that I think the ability to evaluate AI and appreciating its failure modes is probably as important, if not more important, than knowing how to build an AI engine, right? I mean, thanks to all these amazing tools like Codex and Cloud Code and all these really amazing tools, you can go from an idea to a vibe coded prototype pretty easily now. But if you don't appreciate how to evaluate it beyond just the standard metrics or to evaluate its failure modes, then a gap comes in. And that gap can either purposefully or inadvertently lead to organizations buying the wrong tools, misinterpreting the quality of the output, misinterpreting vendor claims about the quality of the data and the model. And then when this misunderstanding happens or misinterpretation happens, if and when there is a system failure, it causes this loss of trust, right? And the problem was not in any particular component, it's in the entire workflow. And so it's not a technical failure as much as a decision making failure. And so what we've seen as literacy gap is it can lead to bad procurement decisions, it can lead to ungovernable systems, it can lead to misplaced trust in these outputs. So my goal with this literacy exercise is to try to educate the community about these potential failure modes so that they can make better choices, procure knowledgeably, and deploy responsibly to be able to help their patients in the way that they are supposed to, and in a way that will get them the right benefit for their patients. So that's kind of my part is not I mean, AI education for building models is all great and there's plenty of it already, but I see a genuine gap in the ability to for how do you build a right rubric for a sniff test that anybody, even if they're not AI experts, can use to be able to meaningfully calibrate if what they are being sold is not snake oil.
Yeah, no, that's really interesting. Are there any nuggets from that conversation that you use, sort of like, things that you might be able to pick up with your sniff test, that you see healthcare and pharma teams aren't able to pick up with their sniff test?
Yeah. So, I mean, my most common question is, well, what is uncertainty accompanying your prediction? And if they can't answer that in a way that's satisfactory, I mean, it doesn't need to be very fancy, right? But if you don't even have an answer to how you do it and what's the basis of that uncertainty quantification, then I know immediately that the numbers are not the entire story. There's more than that under the hood. And then the other question that I like to ask, which is, it's all very nice about where it does well, but obviously not at 100%. You're at a 95 or whatever it is. Where does it fail? And are there patterns to those failures that can help us understand what this model is capable of doing or not capable of doing? Right? So is it attributable to data shift artifacts like instruments and scanners and sites? Is it something more serious about the wrong population for which it is being recommended? And what does it mean in terms of real world evidence for the deployment of what you're predicting about and its translation to actually helping a patient? So, again, that's another part about assumptions that I question and failure modes that I try to understand better. And again, I think you don't need to be an AI engineer per se to ask these basic questions, right? When I go to buy a car, I am not a automobile engineer. Yet there are some basic questions I know to ask. What's its mileage? What tires does it need? Does it drive well in the snow? Right? Simple things, right? I don't need to be an automobile engineer to ask this question. Similarly, when I go to buy my favorite cereal in the grocery store, I'm not a farmer. I don't know the first thing about food processing. Yet there's enough information on that box that when I turn it over, I can say, okay, here's the ingredients, here's where it was made, here's the guidelines it adhered to while producing it. So I can then say, well, it's safe enough for me to consume, regardless of its price point. That is something that I eat. This is something I drive. Both of them are related to my safety. When I use AI to do similar things, how come nobody asked that question? It shouldn't have to be. Don't disentangle the conversation in complex terminology because it should be explainable to anybody who's using it. In fact, tomorrow, your patient is going to come up to you and say, Doctor, why did you use this tool on me? And why would you not use something else? If you can't give a good answer, then I think we are in trouble, right? So I think the vendor has to be held accountable to those important questions. And so any procurement exercise has to be informed from that perspective and not just relying on nice ROC curves or nice accuracy metrics. That's a good start to a conversation, but I don't think it should be at the end. And I think that gap has to be addressed.
Yeah, that makes a lot of sense. That the accuracy is sort of like, should we be having a conversation or not? It's not the end of the conversation. It's the start of the it's the start
Exactly.
of the conversation. Yeah, that makes a lot of sense. And also, as I'm hearing you describe things, as individuals, when we pick up a tool like a pen or something like that, we recognize that we have to learn to hold this in order to ensure that we're able to get reliable letters or numbers out of the pen. But as organizations, there's just a variety of questions that need to be asked, in particular as you're describing about failure modes, to teach the organization how they need to hold that model or that computational tool in order to compensate for the failure modes and ensure that even if the model is 95% reliable, you're able to get near 100% of what you need out of that model, and by compensating for the 5% of cases where the model might fail. So as we head toward the end here, you work in radiation oncology, which has this long history of quantitative models and treatment planning. How does the culture of that discipline, where sort of physics-based models and dosimetry are already deeply embedded, shape how AI tools get received there versus other areas of oncology where the quantitative approaches are sort of less native to the workflow?
Yeah, it's a great question. So I think it's like you said, I'm very lucky to be in a radiation oncology department because their knowledge of physics and mathematics is genuinely very well aligned with the care that they offer the patients, right? So things like segmentation errors or dose planning or the physics of and calibration, every morning or every so often they will calibrate their devices. And all of this speaks to a discipline. I think the key part to remember is that to deploy these tools to the extent that you want to see success, there needs to be a discipline to the calibration. I mean, same thing, right? Even you go to a biology lab. They calibrate their pipettes every so often, right? Somebody comes around and says, "We are calibrating pipettes, come do this." Where does that calibration happen for AI? We talk about drift, right? Like it's a natural thing. It is a natural thing because we leave these things unattended for too long. So I think the key part is to remember that these disciplines, we should definitely think about radiation oncology and the disciplines that have led the way, radiology also, right? Is that they have adopted certain technologies much earlier, and so their hard learned lessons can be very big beacons for how we need to do things in a more principled way. Number one. Number two is to be able to, what will it take to graduate a device from a curiosity to a deployable entity? And so, because they are so facile and they are so well in tune with what it takes to go from a proof of concept to a deployment that can help patients, I think these communities in medicine can become really important fact checkers and guides for how to do things right. So I've learned a lot from my radiation oncology colleagues. Yeah.
Yeah, that's great. Well, I think we'll leave it there. So, Arvind, just want to thank you so much for coming on the podcast today. I really appreciate the time and look forward to connecting down the line.
Absolutely. Thank you for having me and for all the great questions. Thank you.
Arvind, thank you. This was a masterclass in what it takes to move from multimodal data to clinical insight, and why the gap between building AI tools and deploying them responsibly deserves far more attention than it gets. The core takeaway here is that the hardest problems in computational oncology aren't algorithmic. They're about data quality, validation rigor, and making sure that the people who deploy these systems understand them well enough to govern them and use them reliably. You can find Arvind on LinkedIn and explore his lab's work at the University of Michigan, especially if you're thinking about AI literacy programs for your own team. If you know a data leader or a clinical team that's evaluating AI tools for biotech and needs a sharper lens for what's real and what's hype, send them this episode. And if you haven't already, please subscribe so you don't miss what's coming up next. We'll talk to you next time.
And that's it for this episode of Data in Biotech. If you enjoyed the episode, please subscribe, rate, or leave a review in your podcast platform of choice. See you next time.